Hey everyone, today we're going to talk about section 2.5. Now this is the supplement for Math 90. So this is where Math 90 deviates from Math 89 because in pre-calculus and beyond you use this idea of transformations for graphs all the time. It really gives you a lot of information about a graph before you actually graph it. Now one of the tricks of the trade with transformations is that you have to know some shapes of graphs just by looking at the particular equation that you're given. So you're going to have to do some memorization. Let me grab a pen here. So you have the first one, which is your constant function. So this one looks sometimes, if you use y equals c, so y equals, in this case it looks like about 1.75, somewhere around there. And then you have the identity function, which is just y equals x. This is just really a line. And then we start to get into some more fancy graphs. So we have the absolute value function. And the next four graphs, including the absolute value function, those are the ones that you're really going to have to focus on memorizing and sort of knowing where your base graph lives, where those points are. So on the absolute value function, there's going to be 3 points I want you to follow. That's 0, 0, 1, 1, whoops, forgot the 1, and then negative 1, 1. And so on this graph, you'll follow those 3 points. And what a transformation is it just tells you where to move the graph, up, down, left, right, but the basic shape of the graph stays the same. Now, the next one, which is your quadratic, this is a parabola. Notice it's a nice, smooth U shape. And it also has the points 0, 0, and 1, 1. Oops, keep forgetting to write that second one. And then over here, you have negative 1, 1. So notice on the parabola and the absolute value function, sometimes this is called a V graph because it comes to a sharp point versus the parabola, which is smooth and continuous there. We have the same 3 ordered pairs, but the shapes are pretty different. And that comes in just knowing what the equation looks like. So how do you know you have a V graph? Well, you're going to have literally absolute value bars in the graph, where a parabola, you'll just have the highest exponent be 2. So these are the simplest versions of the absolute value graph and the quadratic or the parabola. With the cubic, so the highest exponent is 3, you're going to follow the points 0, 0, 1, 1, 1, 1. And then over here, this guy is negative 1, negative 1. So not the same 3 points. And this you'll sometimes hear referred to as an S-curve. And so again, it's just this smooth sort of, and a smooth and continuous graph. Finish one thought before I start the next. Second thought, if you don't realize the shape of this graph before you start to graph it, those points look like they could line up form a straight line, and you could draw the wrong graph. So big thing here is knowing what the graph looks like before you ever start to graph it, because the points could be misleading if you just try to plug in a point, plug in an x coordinate, get out a y, plug in an x. It doesn't work when you start to get into more sophisticated graphing. And then the last graph we're going to look at is the square root graph. And this sort of looks like, well, it is half of a sideways parabola. And so on this graph, I only have you follow 2 points, 0, 0, and 1, 1. And then we'll talk a little bit more about domain and range of a graph once we start graphing these. So, a couple of things. Note, I'll read the note down here. You must recognize the graphs of the common functions. Graphing by transformations uses the same generic shape but shifts location and size. So what I want to do right now is I'm going to switch. We're going to talk about vertical shifts first. So this is your up-down shifts. And what these do is they move the graph up or down. So the graph that you're starting with up here, these base graphs, down with the sign of the outside constant. And this impacts only the y coordinates of the function. So if you look at example 1, we have our typical absolute value graph. And remember, on this graph, we follow 3 points. And remember, the 3 points are 0, 0, 1, 1, and negative 1, 1. And so if I come in and graph, I have 0, 0, 1, 1, negative 1, 1. And so I'll draw this graph in blue. So now what's the difference? I'm going to switch colors here. What's the difference for this guy? Well, we added 2 in the back of the absolute value. And so what that's going to do is it's going to shift our entire graph up 2 units. And really quick, you can make a t-table. So let's use the same x-coordinates, 0, 1, negative 1, as we do for the parent graph. But what happens when you plug in 0? Well, if I plug in 0, absolute value of 0 is 0, plus 2 is 2. If I plug in 1, absolute value of 1 is 1, plus 2 is 3. And the absolute value of negative 1 is positive 1, plus 2 is 3. So I end up here at 0, 2, 1, 3, and negative 1, 3. And so if you notice, our graph was shifted, our blue graph was shifted up 2 units. That's a transformation. Basically what we're saying is you don't have to do a t-table. You should just know by looking at the plus 2 after the absolute value that that's going to move everything up 2. So real quick, I'm going to switch over to Desmos, which is a graphing calculator. And it's just www.desmos.com. And if you, let's put in absolute value here. Let's go back, backspace, backspace, backspace. And let's do absolute value of x. And there's our typical absolute value graph. And so now, if I come over here and I say plus 2, you see it shift up there, 0, 2. So what happens if I move, say, I put minus 3? Well, what happens is our graph shifts down 3. So if I say minus 1, exactly what you expect. Remember, this is 2, so this is 0, 1. Everything shifts down 1. So the point of this, I'm going to go back to our notes now. And you can, this is a free graphing calculator, just literally www.desmos.com. And you can play around with it just so you start to get a feel for adding and subtracting, multiplying, what happens to these graphs. So now we know, if we come in, and I'll go with a different color now, so I'll go with orange. So this is going to move the original graph down 3 units. And this one moved it up 2 units. So now I can just follow the points. I can just move everything. Literally, I'm just changing the y-coordinates. I'm not moving left or right. So starting from the parent graph, the blue graph, we move down 3. I move 1, 1, down 3 units. He ends up at 1, negative 2. And I move negative 1, 1, down 3 units. So 1, 2, 3. And there's your graph. So it's a different way of graphing because we're using transformations. Meaning we're just looking at the equation and it's telling us what to do. As long as we have a base graph or a parent graph to start with, we know where to move from there. So that is your vertical shift, which moves your graph up or down. And so this always takes place, and you'll see if you look on the next page, you'll know you're doing a vertical shift because you'll have the plus or minus a number after the function, meaning after the absolute value bars or after you use the exponent or after the square root symbol. And then you have sort of the formula here. Y values become y plus c, y values become y minus c if you're moving down. All right, so now the question is, well, how do you move left and right? And that's a good question. So let's talk about horizontal shifts. So horizontal shifts move the graph left or right, and this goes against the sign of the inside constant. So before we had an outside constant, so we did this, that would be considered outside because it's after the absolute. It's literally not inside the absolute value bars. So the difference now becomes this. This is considered x plus 3 inside the absolute value bars. So you're adding or subtracting before you take the absolute value or before you square. And when you do that, you move left or right, depends on if you're adding or subtracting, and you move against the sign, meaning you move opposite what you think. So let's look at this next example. Example number 2, we have a parabola. We know this is a parabola because highest exponent is 2. And we know the points on that parabola that we follow are 0, 0, 1, 1, negative 1, 1, because we memorized that. And we start to graph. So 0, 0, 1, 1, negative 1, 1, and then here's our base parabola. So this guy is f of x. So now let's look at g of x. So for g of x, I'll come in with red. Notice you're adding 3 on the inside. So what do you think that does? Well, let's go look on Desmos. So now I'll come back, erase what we had here, and we'll do parenthesis, and then we have, actually, let's just do x squared. So there's x squared. Now let me do another one. So y equals, or f of x, it doesn't matter, y equals parenthesis x plus 3, and now I'll close it up, squared. So most students, when they first see this, they think, well, I'll move 3 to the right because I told you it was left-right movement, but you actually move 3 to the left. And that's because you're trying to create an equilibrium in here. You're trying to create a 0 in here. Your graph's trying to get its center back. And so you're moving opposite the inside sign. So if you see x plus 3, you're really going to move left 3, not right 3. And if you get x minus 3, you're going to move right 3. So you move opposite that sign on the inside there. So let's go back to the notes. So how is this going to shift? You're going to move 3 units to the left. Again, that's because it's your graph trying to get back its center of 0. So your graph's trying to create a 0 in here. So negative 3 plus 3 would be that 0. So negative 3 is to the left. So that's where your new center is. And then everything moves to the left 3 units. So 1, 1 moves over 1, 2, 3. And this is very visual. You can literally count it out. So, and negative 1, 1 moves 1, 2, 3. I'm going to be off my graph a little bit. And so you get the same shape. You're just moved left 3 units. So what's going to happen for this guy? Well, he's going to move, you got it, right 2 units because you move opposite the sign when you're on the inside. So now I'll come in and do that in green. So let's move right 2 units. So 0, 0. Notice I always start with 0, 0 because that's sort of the center of the graph. Moves right 2 units. Negative 1, 1 goes to 1, 1. And 1, 1 goes over to 3, 1. And so there's your parabola. And it's h of x. So that's your parabola moved right 3 units. So this guy affects your x coordinates. Notice your y coordinates are all the same. They're all at a height of 1 or 0, just as we started with. So that's what this says down here, that if you have x plus c or x minus c inside, that's the notation for inside the function, then you're going to shift. If it's plus, you shift left. If it's minus, you shift right. And your x values change. And this becomes important in the homework because they might say something like this: hey, you have this ordered pair on your graph and you have to shift it. What would this due to that particular point, f of x minus 2. And so in this case, you're saying, all right, well, I would shift right 2 units. And so I would end up where 4-2 would end up at 6-2 because you're adding 2 to the x coordinate. And we'll practice that a little bit more. I know it's a little bit different, but remember, this is a graph. This is not you plugging in points. This is just saying take the original f of x and shift it by subtracting 2 on the inside. Okay, so let's continue. Keep practicing. So switch colors here. For this guy, 2a, use the graph of f of x equals the square root of x to graph g of x equals square root of x minus 2. So on the square root graph, we know it looks like half of a sideways parabola, so we have to memorize that. We have to know that. And we start at 0, 0, and 1, 1. So that's what his graph looks like. And notice he sort of stops. He doesn't go on to the left forever. He goes up forever, but he doesn't go to the left, and that's because you can't plug negatives into the square root. So I can't take -1 because I get imaginaries, and we're not working with imaginaries on graphs. There's no imaginary axis, at least not in this class. So that's why you're sort of you have an end point, if you will, there. So what does this do? What does that square root of x minus 2 do? And so the question you ask yourself is that minus 2 on the inside of the square root or on the outside? And since it's on the inside, you know you're going to have a left-right shift. Now, are you going to shift left or right? Well, you move opposite the sign. So we move opposite the sign. So that means we're going to end up shifting to the positive direction or to the right. So we shift right 2 units. So now I can do that. So I take 0, 0, I move that to 2, 0. I take 1, 1, I move that to 3, 1, and I draw the same type of graph, just shifted right 2 units. And so did you see how quick that was? You didn't have to plug in an x, get out a y. You just have to read the function. And so basically you say, all right, I don't know what square root of x looks like, but now if I just have square root of x minus 2, very similar, I'm just going to take my graph and shift it right 2 units. Okay, so now what's better than one transformation? 2 transformations. So example number 3, we have the graph of f of x is equal to the square root of x, and we want to graph this g of x as the square root of x, or sorry, it's not square root, absolute value of x plus 2 plus 1. So again, we know this is a v-graph. We know what that basic graph has, what points we're going to follow. So what's happening here? Well, start on the inside, order of operations, start on the inside. What is that plus 2 going to do? Well, the first thing he's going to do is he's going to shift left because you move opposite. You move opposite the inside. Inside meaning literally inside the absolute value bars. So you're going to shift left 2 units, and then you're going to have this number right here. And this is going to be, so you move the same as the outside. So that shift is an up-down shift because it's on the outside. And so then I'll write that here, left, right, and this one is up, down. All right, so this guy, we're going to move up 1 unit. So let me draw the original graph, 1, 2, 3. And we have 0, 0, 1, 1, negative 1, 1, and then we have this nice V-graph. Okay, so I'm going to do this in 2 steps because I think that's helpful. So the first thing I'm going to do is I'm going to do the first transformation, which is shift left 2 units. So I'm going to move 1, 2 to the left. So 0, 0 goes to negative 2, 0. Negative 1, 1 goes over to negative 3, 1. and then 1, 1 moves over 2 units to negative 1, 1. And I'm going to draw this as a dashed graph. And if you see me draw as a dashed graph for anybody, that means it's not my final graph. It's an aid to get me to my final graph. So I still have to move up 1 unit, so I'm not done. So I'll come in now, come in with red, and we need to shift everything up 1 unit. So now I'm using the light blue graph because I've done my first transformation, the shift left. Now I'm going to move everything up 1 unit. So negative 1, 1 moves up to negative 1, 2. Negative 2, 0 moves up to negative 2, 1. And then negative 3, 1 moves up to negative 3, 2. And so it's my final graph. So I'll draw him solid. And so this is my final graph. And so that's what your answer would look like. And so, you know, when we did this paper pencil out of the book, all you would see is that final answer typically. You wouldn't see the intermediate graphs. And then really, to be legitimately correct, this graph should also be a dashed graph because he's not really your final graph either. So the only graph that should be solid is your final answer. And so those are your first 2 transformations, your shift up, down, and your shift left, right. So now we have 4 transformations in all. And so the third one we're going to talk about is reflections. So again, we're going to make an outside-inside argument. So the reflection of the x-axis, so about the x-axis, so that means you're literally going to flip over the x-axis, is when there's a negative on the outside of the function. And so this guy will only impact the y-coordinates because if you're up at the, say up here at 4, you're going to flip down to negative 4. You're flipping across the x-axis. The way you reflect about the y-axis, so from the right side to the left side or left side to the right side, is when there's a negative inside the function. So now you're a little more familiar with this inside-outside talk. And this one affects only the, oh, that's a typo. That should be right here. Should be x-coordinates, not y-coordinates. All right, so let's look at this. So for this guy, is that, for example, number 4, we have x cubed, and then we have to graph negative x cubed. And so the question would be, is that inside or outside? And that would be considered outside, because to be inside of an exponent, you have to be literally inside parentheses. So this would be considered inside. And so thus, since this is outside, we know we are going to reflect about the x-axis. Okay, well, let's draw the original graph first. So I'll come in. And remember, this is an S curve, so it has a point 0, 0, 1, 1, negative 1, 1. And again, if you don't know any better, those look like they would graph a straight line, but actually all the points in between start to get curvy. And so it actually looks a little bit like that. And it's, I don't draw any better on the board, so it's just my artistic abilities are limited. But it's an S curve, so you've got it. Okay, so now the shift. So we're going to reflect, and one of the ways that you can think about reflections, I'll do a lighter color here, is just fix this whatever axis you're reflecting about. So for us, we're reflecting about the x-axis. So if you fix that and you just count the distance that your graph is above or below that axis. So this point right here, 1, 1, is 1 unit above the x-axis, so he's going to flip down or reflect down, so he'll end up 1 unit below the x-axis. Now 0, 0 is on the x-axis, and this tablet always does this. So 0, 0 is on the x-axis, so anything on an axis of reflection just reflects back onto itself. Another way to think about this is if you were to fold, if this were a piece of paper and you were to fold it along the x-axis, where would these points fold onto? And so 0, 0 would fold onto himself. This guy 1, 1 would fold down here. So where would negative 1 fold? Well, he's 1 unit below the x-axis, so he would end up 1 unit above the x-axis. And so you end up with this same, and the tails would flip same in the same way. I can't get the arrow on the edge there. There we go. Try that again. There we go. And so the tails would flip across that x-axis also, and that would be your final graph. Okay, so kind of go through that example and see if that makes sense to you. And let's come down and look at what an inside reflection or negative looks like and what a y-axis reflection looks like. So you see here that when you have the outside, the negatives on the outside of the function, so on the outside of the parentheses, outside of the absolute value bars, outside of the square root, that you're going to reflect about the x-axis, and that your y values are really just multiplied by -1. Meaning if they were positive, they become negative. If they're negative, they become positive. Similarly, if you're on the inside, then you reflect about the y-axis, and now your x values, if they were positive, become negative. If they're negative, become positive. So let's look at example number 5. So I'll switch colors here. So we have a square root function, and on the square root function, remember, we follow those two order pairs, 0, 0, and 1, 1. So I'll draw in the graph here. 0, 0, 1, 1. And let's do that as a dashed graph since it's not our final graph. So that's sort of the parent graph, the base graph. And so what does this negative on the inside of that square root do? So this guy here, so he's definitely on the inside because he's literally inside the square root. Well, since it's a multiplication, he's going to reflect the original graph about the y-axis. So now your axis of reflection is the y-axis. So what's going to happen to 0, 0? Well, he's your axis on your axis of reflection, so he stays exactly the same. But what happens to 1, 1? He's going to flip across the y-axis, and so he's 1 unit to the right of the y-axis, so he'll end up 1 unit to the left, and you can see this tail's going to flip around to this other side, and so we end up with the square root function moving to negative infinity instead of positive infinity as far as the x-axis is concerned. And so now that's sort of a good time to talk about domain and range also. What is the domain of this graph? What is the range of this graph? So remember, with your domain, it's just the furthest to the left, furthest to the right, and so we're looking at this light green graph. Well, we know the furthest to the right this graph goes is 0, but to the left it goes on forever. So your domain, and in this case I'm going to use interval notation, and interval notation just says, okay, tell me where your leftmost point is. So for us we'd say negative infinity, because I can't draw, there's no line I can draw over here to the left, it just keeps going to the left. And then we go up to 0. Now, with negative infinity, we can't include that because it's not a number, so you never use brackets on infinities, only parentheses. But with 0, my graph does take on the point 0, so this is how we use interval notation. So interval notation. And so we go from negative infinity, and just you start from the smallest x value or y value to the largest. So negative infinity, the comma, notice this is not an ordered pair, this is interval notation. Negative infinity up to 0, close with a bracket, because we actually take on that value and we stop there. So that's our domain. Now what's our range? Well, our range, let's switch colors here so you can see it. The bottommost point of this graph is right here. And so we start literally at 0 as far as the y-axis is concerned. Now, this graph keeps going up and up and up forever and ever and ever, so it goes up to positive infinity, meaning it takes on all y values above 0. And again, we close with a parenthesis. So that's your interval notation, and we'll practice that a little bit more. Now, if I go back to example number 4 and I talk about domain and range, I just wanted to get the graphing out of the way a little bit more before I brought in this piece of the puzzle. The domain and range for polynomials that go in opposite directions like this, meaning the ends go in opposite directions is what I was saying there. The domain is going to be negative infinity to infinity, and the range is negative infinity to infinity, meaning it goes left and right forever, and the graph goes up and down forever. There's no limit. There's no stop point. And so I couldn't draw those lines even if I wanted to. And so in that case, that's where you get actually what's considered the easiest domain and range, where there's no limitations, just negative infinity to infinity for domain, and then negative infinity to positive infinity for range. All right, so I know it's a lot of information. This is the bridge to Math 90 right here. Okay, so example number 6, we have a couple of transformations going on, and you have to pay attention to multiplication versus addition and subtraction. So with number 6, we're back to that same square root function, 0, 0, and 1, 1. So now what are your transformations? And we're going to work inside out. So this guy, you're adding on the inside. And so if you're adding on the inside, that's a left-right shift. If you're adding or subtracting on the outside, that's an up-down shift. And so the negative on the outside multiplying, that's your reflection. So this is going to be a reflection, and then this is going to tell you you're moving left or right. And then we kind of get into looking exactly where they're located and what the numbers are to tell us. So on the inside, we're going to shift. Is it going to be left or right? Good. We're going to move left 3 units because we move opposite the sign. You go opposite. Now, the next one is that negative on the inside or the outside of the square root. And since it's on the outside, we're going to reflect about the x-axis. If it were on the inside, we reflect about the y-axis. And so what would inside look like? Inside reflection would have looked like f of x is equal to negative x plus 3, where the negative literally is on the inside, but that's not what we were given. So let's work with what we have here. So we have our original, let me draw some grid lines here. So we have 0, 0, 1, 1, and that's our square root function. And now we're going to shift that left 3 units. So I'll do that first. I'll go with orange. So I'm going to go left 1, 2, 3. There's 0, 0 goes to negative 3, 0. And 1, 1 goes left 1, 2, 3 to 2, 1. And I'm still going to draw that as a dashed graph because it's not my final graph, because I still have to do a reflection. So now we're going to reflect about the x-axis. So I'll come in, do that in red. If I reflect about the x-axis, negative 3, 0 is going to stay right there. And then negative 2, 1 is going to reflect down. And so now you'll have this graph that's reflected downwards. And I guess a good question would be, what's the domain, what's the range? So the domain here, well, this graph has an endpoint. Do you see that right there? So it starts at negative 3, but then it goes to positive infinity as far as the x values are concerned, the x-axis. Now the range for this one, you have to start at the bottom. Well, the bottom, this graph keeps going down forever, so it would be negative infinity up to the highest point, which that keeps turning orange, up to the highest point, which would be 0 for the y-axis, meaning if I were on the y-axis and I look over, the highest y value, the largest y value is 0. So that would be your range. Okay. Now, one more transformation, just one more. And that is multiplying by a number, not just a negative 1. So, vertical stretching and shrinking. Sometimes shrinking is called compression. And we can talk about that. It just depends on the textbook. So for vertical stretching and shrinking, this shrinks a graph according to the coefficient of the leading term, impacts only the y-coordinates of the function. So for this guy, notice we have some multiplications in the front. And so I'll come in. We know this absolute value graph, so we have 0, 0, 1, 1, and negative 1, 1. And let's graph that guy. So here's 0, 0, 1, 1, negative 1, 1. And so we'll put him in green. That's f of x. So the question is, what's going to happen when you put numbers, multiply? Notice you're not adding. You're multiplying by a coefficient. So let's go back over to Desmos and kind of explore this idea. So I'm going to get rid of this guy. So I'll call him out. And let's go back to absolute value because that's what's in our example. And so there's our absolute value graph. You can kind of see that. It's entered at 0, 0. Here's 1, 1. Then there's negative 1, 1. And you can kind of follow the graph. There's negative 1, 1. And then all these other points along the graph. And then there's 1, 1. So now, if I put a number in front, watch what happens. Say 5. That's called a stretch, meaning imagine you pull the top of your graph up really tight, like a rubber band, and so you're basically making your graph taller. So where you were at 1, 1, you are now at 1, 5. So follow the graph. So try to get right on there. There's 1, 5. And so what happens is this multiplies your y-coordinates by whatever number is in front. And so similarly, it also happens with negative 1, where you had negative 1, 1, you're now at negative 1, 5. Notice 0, 0 doesn't change. So that's because you multiply your y-coordinates, and your original y-coordinate was 0. So 0 times 5 is 0. So what happens is anything on that x-axis gets fixed on the x-axis, but all the other numbers, all the other y-coordinates get multiplied, and so you feel this stretch. So what happens if we do, say 1/2 in front? Because there is sort of a different feel. So there's the green graph is that original y equals the absolute value of x, and so if I come in front, and I'm going to just do a decimal to make my life easier. Look at what happens if you do 0.5 or 0.1 or 0.2 or 0.333. Oops, you don't need 2 decimal points. That's called you shrunk it, or a compression. Imagine you push down on the graph and it's a lot wider. So another way to say this is if you have a number and you're multiplying that's larger than 1, a coefficient, your graph is going to stretch. If you have a number less than 1, a fraction of some sort, or a number you could write as a fraction, or a number smaller than 1, ignoring sign, because sign just tells you if you're reflecting about which axis, then you get a wider graph or a compressed graph. Now the trick to graphing these is you have to notice you're multiplying the y-coordinate by whatever this number is in front. So for instance here we normally had that 0.11, so I'll kind of follow along, and so when I get to x equal 1, it's not at 1 anymore, it's just at 1.3, so whatever that coefficient is, because that's what your y value becomes. Okay, so now I'm going to go back to the notes. So what is going to happen here with this guy, I'll go with a light green, is you're going to stretch. Wait, it's not one to write. Let's go up here. Stretch by 2, which means multiply the y-coordinate only by 2. Okay, so what were my y-coordinates? Well, remember, here's your y coordinates right here. So I'm going to stay with an x-coordinate of 0, but if I multiply by 2 on the y-coordinate, I still get 0. And then if I stay with an x-coordinate of 1, multiply his y-coordinate by 2, I end up with 1, 2. And then same thing here. If I multiply negative 1, the negative 1 x-coordinate, his y-coordinate was 1, multiplied by 2, I end up with 2. So another thing that I'll do when I'm teaching this is I'll say, all right, these were my original points. 0, 0 stayed at 0, 0, but 1, 1 goes to 1, 2, and negative 1, 1 goes to negative 1, 2, because you're multiplying by 2 times 2. And so now we get this sort of taller or stretched absolute value graph. And then similarly with the 1/2, it's going to be the same idea. So with this guy, you're going to shrink or compress, it just depends on the textbook, by 1/2. And that's because this is a number less than 1. Again, ignoring the signs. The negatives just tell you to reflect. So that means I'm going to multiply the y coordinates by 1/2. These are the originals. And so what happens is 0, 0, well, when I multiply, remember these are your y coordinates. When I multiply by 1/2, I just still end up at 0, because 0 times 1/2 is 0. But 1, 1 goes to 1, 1/2, and negative 1 goes to negative 1, 1/2. So 0, 0 stays there, but I'm at 1, 1/2, negative 1, 1/2, and so I end up with this really wide graph, or a compressed graph. And so that's the last transformation. So we have 4 different transformations. We can add or subtract on the inside or outside. We can multiply by a negative on the inside or outside, and then we can multiply by a number on the inside or outside. And those all give us different results. So let's look at one more example, and then I'll sort of summarize all those transformations. And so here, with number 8, we have a couple transformations happening. So we're going to use x squared, and remember the graph of x squared is a parabola with points 0, 0, 1, 1, and negative 1, 1. And he looks like a nice smooth U shape. So what are the transformations going to be? Well, you work inside out. So this first, the -1, is going to shift the parabola right, because you move opposite the sign, right 1 unit. And then the 3 on the outside is going to stretch the y coordinates by 3. So what does that mean? Well, let's do the first shift first. So I'm going to shift right 1 unit. So 0, 0 goes to 1, 0. Negative 1, 1 goes to 0, 1. And I'm just moving everything over right 1 unit. And I'm going to draw that as a dashed graph because I still have to. So that's done. Now I have to stretch the y coordinates by 3. So I'll come in with a different color here so you can see that. We'll do red. So that means multiply the y coordinate by 3. And this will be from the dark blue graph because we've already done the shift right. So the y coordinate of 1, 0 is just going to be, so the y coordinate is 0 because that's 1, 0. So he stays right there at 1, 0 because if I multiply that y coordinate by 3, it doesn't change. But now this guy on the rightmost point, the negative, or the 2, 1, so that's 2, 1. When I multiply him by 3, he goes to 2, 3. You fix the x coordinate, you're just multiplying the y coordinate. So I'm up here at 2, 3. And then the same thing with this guy, I'll kind of come down here. He's at 0, 1. He's going to go to 0, 3 because you're multiplying the y coordinate. So 0, 3. And there Here's your final skinnier or narrower stretched graph. Okay, so I know it's a lot to take in. Putting it all together. So there is an order of operations when it comes to transformations. So a function involving more than one transformation can be graphed in the following order. All right, so what's that order? First, you do any horizontal shifts first. So horizontal shifts are the inside addition or subtraction. And in this case, you're affecting the x values or the x coordinates. Oops. And you're going to shift, you're going to go opposite the sign. All right, 2, you're going to do any stretching or shrinking. So this is the multiplying. And so in this case, your y values are multiplied. Then you're going to do any reflections. And in this case, there's going to be a sign change in x. Actually, I should say on x, or y, depending on if the negative is on the inside or the outside. And then fourth, or the last one you always do, is your up-down shifts or vertical shifts. And so with these shifts, your y values change. And so you see that's important, because if you're multiplying your y values and you shift up or down first, you're going to get the wrong answer. So you want to do stretching or shrinking first. So your y values shift. And here you go, you shift same as the sign. All right, so that's sort of your summary, and I put all of the different rules here and the effects on the points, so you had them all in one place. I had kind of scattered them about the notes here. So there's your 8 shifts, and it's really 4 different shifts, and I should say that it's just a matter of if you're positive or negative, or where you're negative. So these 2 are your up-down shifts, your vertical shifts. These 2 are your horizontal shifts. These 2 are your stretching or shrinking or compressing, as they say, depending on if you are greater than 1 or less than 1. And then these are your reflections. And so that just depends on if you're outside or inside. So that is section 2.5 part 1. I'm going to pause it here because this is a long video. It's a long section of material. Do watch both videos though before you do the homework, because I couldn't split the homework up quite as nicely as the notes get split up. I didn't have as much control over that. So go through, take a quick break, and then come back and watch part 2 to be continued.